Imagine you're at a buffet with a stack of plates. You pile them up one by one, but you can only take the top plate when you're ready to eat. This simple scenario is actually a powerful concept in computer science known as a stack. Welcome back, everyone. Last time we explored arrays. Great for their simplicity and direct access, but they have their limits. Today we'll dive into a data structure that's perfect for managing data in a specific order: the stack. Think of a stack as a real-life stack of plates. You can only add or remove plates from the top of the stack. In the world of data structures, this is exactly what a stack is: a collection of elements where you can only add or remove items from the top. Stacks operate with two main actions: push, which adds an element to the top, and pop, which removes the top element. Think of it like adding or taking plates from a stack. You always deal with the top plate. Stacks follow the last in first out principle, or LIFO. This means the last item added to the stack is the first one to be removed. Just like the top plate in our stack, it's the first one you take when you need a plate. Stacks are versatile tools in computing, ideal for situations where you need to manage data or tasks in a last in first out order. Stacks are perfect for reversing the order of elements, like backtracking in algorithms. Now let's explore how stacks help manage function calls in a program. Here's a basic example where the main function calls function A and function A then calls function B. When the program starts, main is pushed onto the stack. Next, function A is called, adding its frame to the top of the stack. Then function B is called, which is added to the top of the stack. Once function B completes its execution, it is popped off the stack. Function then completes and its frame is also popped from the stack. Finally, main completes its execution and is popped from the stack, clearing it and ending the program. Let's see how a stack is useful in backtracking. Imagine there is a maze with different chambers connected by paths. Our explorer wants to find a gem hidden inside one of these chambers. As the explorer enters a new chamber, we push the chamber's label onto the stack. He keeps exploring until he hits a dead end. When the explorer hits a dead end, it backtracks to the previous chamber, popping the last chamber from the stack. After finding the gem, the explorer returns to the entrance, popping each chamber of the stack until it's empty. The stack efficiently manages the explorer's path, ensuring all routes are explored until the gem is found and explorer returns to the entrance of the maze. This is how stacks are crucial in backtracking algorithms. Applications like text editors rely on stacks to manage undo operations, allowing you to revert changes easily. Stacks are crucial in computing, managing tasks in last in first out order. They streamline function calls, enable undo operations, assist in backtracking, and a lot more. Their simplicity and efficiency make stacks an essential tool in many applications. Beside push and pop, what we already saw earlier, there are two more key operations in stack, namely peek and IsEmpty. Let's explore the operations of a stack. Push adds an element. Pop removes the top element. Peek views the top element without removing it. And IsEmpty checks if the stack is empty. Notice we focus on what the operations do, not how they're implemented. That's why a stack is considered an abstract data type act. As a user, you don't need to know the internal workings. It follows the last in first out. While ADT focuses on what the operations do, data structure focuses on how to implement them. Let's dive into the implementation now. There are two primary ways to implement a stack. One is using an array and another is using a list. We'll start with an array-based stack. In this series, we are only discussing arrays with fixed size. We use a variable called top to keep track of the stack's topmost element. When the stack is empty, top is set to -1. Pushing an element adds it to the top of the stack. In memory, this inserts the element at the top index of the array. This is efficient and takes constant time, big O1. Stacks can grow as needed in theory, but an array-based stack has a fixed size. Trying to push more elements than the array can hold causes a stack overflow error, indicating no more elements can be inserted. Popping removes the top element from the stack. The element remains in memory but is considered removed from the stack. The top is decremented by 1, making the operation constant time, big O1. Popping from an empty stack results in stack underflow and error, indicating there are no elements to remove. Peek allows us to view the top element without removing it, keeping the stack state unchanged. This operation also takes constant time, big O1. IsEmpty checks if the stack is empty. It returns false if the stack has elements and true when top is -1. This simple check is performed in constant time. These operations push, pop, peek, and IsEmpty define our interaction with the stack, ensuring data management in a last-in, first-out order. We have journeyed through the foundational concepts of stacks, understanding its last-in, first-out principle, real-world applications, abstract data type properties, and finally, how we can implement a stack using an array. In our next session, we'll explore the role of stacks in more depth. We'll see how stacks handle different expressions and understand the advantages and disadvantages of using stacks in various scenarios. Remember, understanding data structures like stacks not only strengthens your problem-solving skills, but also opens up new ways to think about organizing information. Stay curious, keep exploring, and keep stacking your knowledge. Happy coding!